Hello students. Now we discuss the chapter vector calculus, in which first we are taking vector differentiation. So before go through the syllabus, we first discuss the basic concept in briefly, how we define the position vector. Okay, so here in this diagram, in this figure, we have 3D three-dimensional space having x-axis, y-axis and z-axis. So here in this plane we consider a point P, okay, P of x, y, z, and then when we connect this point to the origin, so we join this O and P, okay, then that OP, so that we denote as a OP bar. So this is called the vector OP, and this is called position vector of a point P, and we write this position vector joining the points O and P as OP bar equal to, or vector OP equal to, xi plus yj plus zk. So this I is the unit vector along the x-axis, j is the unit vector along the y-axis, and k is the unit vector along the z-axis. Okay, this is the way we write the position vector in a plane. Okay, taking one simple example. So suppose the point P is um, having the coordinates -3, 2 and 1. Then we write the position vector O and P. We write the position vector OP as -3i plus 2j plus 1 into k. Okay, this is the way we write the position vector, and the length of this position vector, the length, okay, or we can say it's a magnitude, the length of this vector OP, okay, so that we write as magnitude of that OP is square root of -3 square plus 2 square 4 and 1 square. So this is the square root of 14. So this square root of 14 represents the length of the vector OP. Okay, and any point P of xyz in space in which x coordinate, for example, just -3 is a x coordinate, so that represents the distance of the point P from the origin along x-axis. Okay, that is -3 is the distance, okay, from the origin to that point P, right? Similarly, suppose 2 is a y coordinate, why this 2 represents the distance of the point P from the origin along y axis. Similarly this 1. Okay, so this is the some brief introduction about the position vector. Now we take the definitions, scalar and vector fields. Okay, so this is our actual syllabus, scalar field and vector field. So here the definition is, a scalar point function is a scalar. So scalar and vector, these definitions already you know. So scalar which have only magnitude. Okay, so here this scalar point function is a scalar which is real valued function to every point in space. Okay, a scalar point function is also referred to as a scalar field. Okay, so this is we take one simple example. The temperature of a swimming pool is a scalar field. Okay, as you know, the temperature, it doesn't have direction but it has a magnitude, so this temperature is an example of the scalar. Okay, for a swimming pool, the temperature which gives the scalar field. Okay, to each point we associate a scalar value of temperature. At every point in a swimming pool we can take the temperature. Yeah, and the function we write as a x square, y square, z square. This is the one example of the scalar function, and also x plus y plus z. Okay, so this is a example of the scalar field. Now the vector field is a vector point function is a vector. So vector is what? It has both magnitude and direction. So whose components are real valued function to every point in space. Okay, is vector point function is also referred to as a vector field. Now the example for this is the water flow in the same pool is a vector field. When there is a flow of water in a swimming pool, so it has a direction and also magnitude. So this is the example of the vector field. To each point we associate a velocity vector. So when there is a flow of water, so we can calculate the velocity, so which gives the both the direction and magnitude. And this is the way we write the vector function, that is x square I plus y square j plus z square k. So this is the vector function. Okay, so these are the definitions of scalar and vector fields. Okay, now we take some other um, useful results, that is vector differential operator. So that we denote as a del. So this we read as a del, the notation, and this we define as the del vector differential operator we define as dou by dou x into I plus dou by dou y into j plus dou by dou z into k. So this is called vector differential operator del, and this also we can represent as a summation dou by dou x of I. Okay, some in a notation we can write as a summation dou by dou x into I. So that gives dou by dou x I plus the extension way plus dou by dou yj plus dou by dou z k. Okay, when this differential operator is multiplied by a constant vector a, then we write as a this constant vector a dot del. So that we write as this is the dot product a into I, a dot I into dou by dou x plus this means this vector a we multiplied to every term. Next is the Laplacian operator del square. The Laplacian operator, so that we write as a del Laplacian operator as a del square, and is defined as del square as dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay, this is the we define Laplacian operator. Now the important definition is gradient. So gradient of a scalar point function. So here pi of x y z, so this is the scalar function, so which is a continuous differential scalar point function. Then the gradient of pi we write as grad, simply we write as a grade of pi, we read this as grade of pi or simply grade pi, and this in the notation we write as a del pi. So del pi means it's a gradient of pi and is defined as dou pi by dou x into I plus dou pi by dou y into j plus dou pi by dou z into k. Okay, so this is called gradient of a scalar point function. Okay, when we take the gradient of a scalar point function, what are the results we get? So when we take, so where pi is a scalar function, when we take the gradient of this pi, so the result will be a vector point function. Okay, this point you remember. And if pi is a constant, means that scalar function, when scalar is a that's a constant, then the gradient of pi equal to 0. If there is a constant, then we keep the constant c outside, then we calculate the gradient of pi. And this is one more result that is called directional derivative. So directional derivative of scalar function pi of xyz along a given direction a. So this is the vector a, So directional derivative is what? It's a rate of change of the function pi, okay, with respect to x, y, z, with respect to all the three variables, and which is given as gradient of pi, that is del pi dot n cap. So this n cap is a unit vector, gradient of pi dot n cap, this is a dot product, and this n cap we define as vector a divided by magnitude of vector a, okay. And also directional derivative is maximum along the del pi. So the rate of change of that function pi is maximum along gradient of pi. And also this gradient of pi is a vector normal to the surface pi, and this del pi divided by magnitude of this del pi is a unit vector normal to the surface, okay, and is denoted by n cap. Okay, so these are the some important results in the gradient of pi. Now we take some examples finding gradient of pi, gradient of the scalar function, and also finding the directional derivatives. Okay, the problems are very simple here. So here the scalar function is given x square y plus y square z plus z square x. The scalar function is given. Now we have to find the gradient of pi. So del f, sorry, it's a function f is given, we have to find the gradient of f. Okay, now so this del differential operator is given by dou xi plus dou by dou yj plus dou by dou zk and multiplied by the function f. Okay, now this we multiply taking dou by dou x of the function f into I plus dou by dou y of the function f into j plus dou by dou z of the function f into k. When we differentiate partially with respect to x, so we treat y and z as a constant. Similarly, when we differentiate partially with respect to y, we treat x and z as a constant. And when we differentiate partially with respect to z, we treat x and y as a constant. So following this, keeping this I, dou by dou x of f with respect to x, treating y and z as constant, differentiation of x square is 2x and y constant as it is, plus differentiation of y square z with respect to x. So both y and z as constants, so it becomes 0, then plus z square x, differentiation of z square x with respect to x is z square, okay, x is 1. Similarly with respect to y we do, keeping this j here, differentiation of x square y with respect to y is x square constant as it is, y is 1, plus differentiation of y square is 2y into constant z, then differentiation of z square x is 0 because both z and x are constant, right? Then in plus k, then with respect to z we do differentiation of x square y, both x and y as constants now, because with respect to z we are doing, so this becomes 0. Then with y square z with respect to z is y square, z becomes 1. Then differentiation of z square x is 2z x. So this is gradient of the given function f. Okay, so very simple problems we have. Now we take some other problem. Okay, such kind of problems, these are very simple, you can do this. Now we find the unit vector normal of the function x square plus y square minus z at some particular point -1, -2 and 5. So the given function f is x square plus y square minus z. Then to find the unit vector normal, first we have to find the gradient of f. Okay, so this gradient of f is given by dou f by dou x into I plus dou f by dou y into j plus dou f by dou z into k. Okay, so now f with respect to x, 2x, y and z are constants. Now f with respect to y is 2y into j. Now f with respect to z is minus 1 into k. Now at the point minus 1, minus 2 and 5, gradient of f becomes putting x equal to minus 1, y equal to minus 2, z equal to 5. So z is not there. We put x equal to minus 1 and y equal to minus 2. It becomes minus 2y minus 4j minus k. Okay, now the required unit vector normally is given by n cap equal to, this is gradient of f divided by magnitude of gradient of f. So gradient of f is minus 2i minus 4j and minus k, taking minus common, then magnitude of this is square root of minus 2 square 4 minus 4 square is 16 plus minus 1 square is 1, right? Then this on simplification, minus of 2i plus 4j plus k divided by square root of 21. So this is the unit vector normal at the point minus 1, minus 2 and 5. Okay, similarly we can try some other problems. Now the next type of problems, that is finding the directional derivatives. Okay, so the definition already we discussed in the note. Find the directional derivative of the function pi x square yz plus 4xz square at 1 minus 2 minus 1 along the direction 2i minus j minus 2k. Okay, see, as already we defined the directional derivative is gradient of pi. We have to first find the gradient of pi, then we have to find the unit vector n cap using the given direction a, then we take the dot product of these two, so that gives the directional derivative. So in our problem pi is given, so direction vector is given a. Okay, and at some particular point we have to find out the directional derivative. See here, so pi is given, the vector along the direction is given 2i minus j minus 2k. So at this particular point we have to find out the directional derivative. So first, taking this pi, we find the gradient of pi. Okay, dou pi by dou x into I plus dou pi by dou y into j plus dou pi by dou z into k. Now this gradient of pi, okay, so already we discussed that. So this is the result. Okay, then at the point 1 minus 2 minus 1, putting x equal to 1, y equal to minus 2 and z equal to minus 1. So this is the gradient of pi at this point. Now we find the unit vector along the direction 2i minus j minus 2k. Taking this vector, we find the unit vector n cap, that is 2i minus j minus 2k divided by magnitude of this vector. Magnitude of this vector is given by 2 square 4 minus 1 square 1, then minus 2 square 4. Okay, so our unit vector is 2i minus j minus 2k divided by the square root of 4 plus 4 plus 1, 9 is 3. Therefore the required directional derivative is, that is gradient of pi dot n cap. So our gradient of pi is 8i minus j minus 10k, and this is the unit vector. So this we have to take the dot product. So do you know how to find the dot product of the two vectors? Keeping this 1 by 3, then dot product of these two vectors, that is 8 into 2 plus minus 1 into minus 1 plus minus 10 into minus 2. So simplification, 37 divided by 3. So 37 divided by 3 is the directional derivative of the function pi. Okay, now similarly you can try some other problems. Now in the same directional derivative, we have one different problem where the direction, see here, I read the question, find the directional derivative of f, the function is x square y square z square, okay, at the point 1 minus 1 1 minus 1 in the direction of the tangent. See here, the vector is not given directly, the direction is not given directly. So here, to find the directional derivative, first what we need to do, we find the gradient of pi. So gradient of this f, so here f and gradient of pi is, so here we found, okay, for we differentiate f with respect to x partially, this is the result, then with respect to y, then with respect to z. At the given point 1 1 minus 1, putting x equal to 1, y equal to 1 and z equal to minus 1, so we get a 2i plus 2j minus 2k. So this is the gradient of f at the point 1 1 minus 1. Okay, now we have to find the n cap. So we found the gradient of f. Now we have to find the unit vector n cap. So the direction is what? Here the direction is the tangent to the curve. We have to find the tangent to this curve x, y and z. So that how we have to find. See, so vector r, so that we can take as a xi plus yj plus zk. So x is e raised to t, y is 1 plus 2 sin t and z is t minus cos t. Okay, so this is the given vector. Now we have to find out tangent. So tangent is given by dr by dt. Okay, so this dr by dt gives the tangent. So this dr by dt gives e raised to t, differentiation of e raised to t is e raised to t, then differentiation of 1 plus 2 sin t is 2 cos t into j, plus differentiation of 1 minus cos t is 1 plus sin t into k. This is the tangent vector. Now we have to find out unit vector at the point 1 1 minus 1, but we have in terms of t, right, the values of x y z are given. So these x y z, or we can take any x you can take, or y you can take, or z, we have to find out t. So how we have to find out t? Because you know why we are finding value of t, we have a tangent in terms of t, right? So therefore our x is e raised to t, x is e raised to t, y is 1 plus 2 sin t and z is t minus cos t. Okay, so what is x? 1. So e raised to t equal to 1, y equal to 1 plus 2 sin t, y value is 1, then z is t minus cos t, which is minus 1. Take any of these equations and you can find the value of t. Taken the simple equation e raised to t equal to 1, right? Then taking log on both sides, t value t equal to log 1 is 0. Therefore the value of t is 0. This t equal to 0 satisfying all the equations. When you take t equal to 0, so we get 1. See here, this you can check. When t equal to 0, e raised to 0 is 1, yes. When t equal to 0, sin 0 is 0 is 1. When t equal to 0, 1 minus 1, t equal to 0 minus cos 0 is 1. So minus 1 equal to minus 1. All the equations are satisfying. Now dr by dt at t equal to 0 is I plus 2j plus k. Putting t equal to 0 in this dr by dt, t equal to 0, we get the direction. We get the direction I plus 2j plus k. So along this direction we have to find out the directional derivative. So from this we have to find the unit vector. So unit vector is given by I plus 2j plus k divided by magnitude of that, that is square root of 1 plus 2 square 4 plus 1 square 1. So this is the unit vector. So therefore the required directional derivative of the function f along the tangent. So this is the dr by dt. Along this tangent, it is given by gradient of f dot unit vector. Okay, so this is del f, already we found, that is 2 into I plus j minus k, then dot, this is the unit vector, right? Taking the dot product of these two, we get the answer 4 divided by square root of 6. Okay, similarly we can find some similar example. Okay, thank you.